This lecture is on homomorphisms. The first thing we have in this discussion is the definition of homomorphism. You should copy down the definitions and theorems of each section of the textbook. You can stop this tape at any time and copy the definitions down and then continue. And also with the examples, you should do the same. You should copy down the examples and have them in your notebook. This is definition 3.27, and this definition includes the definition of homomorphism, endomorphism, epimorphism, and monomorphism or monomorphism. Let G be a group with respect to operation circle asterisk, and let G prime be a group with respect to operation square asterisk. So these two operations can be different or they can be the same. For example, the first operation could be possible or ordinary multiplication, and the second operation could be ordinary addition, or they can be the operation defined in different ways. A homomorphism from G to G prime is a mapping phi that maps G into G prime. So that's the definition of homomorphism. Is a mapping phi that maps G into G prime such that phi of x, phi of the quantity x, circular operation y equals phi of x, square operation asterisk phi of y. So this means that the operation is preserved through the mapping. And once again, phi is the function that does the mapping, and phi would be the homomorphism, if this is true. And this is for all x and y in G. So x and y are members of the set that we're mapping from. Now, that's the definition of homomorphism. G and G prime are just two groups. They don't have to be the same. But the Dake's definition, the definition of endomorphism, is slightly different. If G is equal to G prime, the homomorphism phi is an endomorphism. So an endomorphism is a special type of homomorphism. If the two sets are equal, or the two groups are equal, if they have the same elements, then not only do we have a homomorphism, but we also have an endomorphism. Phi would be an endomorphism. A homomorphism phi is called an epimorphism if phi is onto. So the function does not have to be onto to be a homomorphism. If this property here holds true, the function that does the mapping, which is phi, is an homomorphism. If it's a homomorphism and is onto, then it would be considered an epimorphism. Phi would be considered an epimorphism. So as you can see, for an epimorphism, phi would have to also be a morphism, homomorphism, but not necessarily an endomorphism. Endomorphism, the two sets are the same. It's like mapping a set into itself. Okay, and last but not least, a monomorphism Phi is a monomorphism if phi is 1 to 1. So once again, for homomorphism, phi does not have to be onto, it does not have to be 1 to 1. But for an epimorphism, it has to be onto. For monomorphism, it has to be 1 to 1. So those are the definitions that we have in this section. Now, next we have example 1. Example 1, for fixed integers, the fixed integers n greater than 1, consider the mapping phi from the additive group Z to the additive group Z sub n. Now this mapping, you're mapping from the integers. You're mapping from the integers to modulo n. And you're looking at the classes of modulo n. And you're mapping once again from the integers to modulo n. Also, addition. You have addition for both groups. Z is like G in our definition, and Z sub n is like G prime in our definition. And once again, phi maps Z into Z sub n, and operation, both operations are addition. That means the circular asterisk that we had is addition, and the the square asterisk that we had is addition. So phi is defined in this way. Phi of x is equal to phi of x, or the class x. Phi of x equals class x. So that means that x is in z. X is an integer, and any value of x that's in z that's an integer is being mapped into that same x as far as the class is concerned. For example, 0 would be mapped into the class 0. 1 would be mapped into class 1, and so forth and so on. Where class X is the congruence class in Z sub n that contains X. From the properties of addition in Z sub n, section 2.6, it follows that phi of the quantity x plus y is equal to the class x plus y. And that's the property that we had when we discussed classes. And of course, this is equal to class x plus class y, which is the same as 5x plus 5y. So thus we have illustrated the property that shows that we have a homomorphism, that phi, the mapping from Z to Z sub n, is a homomorphism, because this property is obeyed. Phi, the quantity x plus y equals 5x plus 5y. So this is what you have to do in the problems at the end of the section, of this section, to show that you have you have a homomorphism. You have to go through this process. Thus, phi is a homomorphism. It follows from the definition of Z sub n that phi is also onto. So remember, onto, you have to show that everything in what we usually call the range, is, everything comes from phi, from a function of whatever you have in the domain. So all of those values, just like class 2 in the range, would come from the integer 2 in the domain. Class 3 in the range would come from the integer 3 in the domain. So you can get everything in the range by using phi. So it would be onto. So since phi is onto, in fact, it is since it's onto, we can go back and read the definition. Look what we said for onto. Oh, over here it is. It tells us right here. It follows from the definition of Z sub n that phi is onto. So phi is, in fact, an epimorphism from Z to Z sub n. And that's what we said in the definition. We said that if the homomorphism is onto, then it's also called an epimorphism. And of course, since phi of 0 is equal to phi of n, which equals to the class 0, and this is what we would have in modulo n. In modulo n, phi of 0 would be the same as phi of n. For example, if we had mod 4, phi of 0 would be the same as phi of 4. They both would be equal to class 0 in Z sub n. Then phi is not 1-to-1. Phi would not be 1-to-1, and hence not a monomorphism. So remember, for 1-to-1, you have to have uniqueness for your elements for 1-to-1. And basically, usually we have everything in the range being used and everything in the domain being used. And we do have uniqueness. No ordered pair would have the same first component. Of course, it's the same second component also for 1-to-1. All right, let's look at example 2. So that's example 1. And that's how you show that you have whether you have a homomorphism, epimorphism, monomorphism. Example 2. For two arbitrary groups, G and G prime, let E prime denote the identity element in G prime, and define phi such that phi maps G into G prime by phi of x equals E prime for all x a member of G. Then for all x and y in G, phi of x multiplied by phi of y, this is ordinary multiplication, is equal to E prime times E prime, because each element that's in G phi of each element that's in G is equal to E prime. That's how phi is defined. It maps all the values that are in G into that one value that's in G prime, which is the identity that's in G prime. So, which means 5x times 5y. 5x would be E prime, 5y would be E prime. And since we have groups, since G prime is a group, that means that we always get an element that's in G prime. Since G prime is a group, and since G is a group also, it's closed. G prime is closed and G is closed, which means we have to get E prime if we're in G. And of course, that would be the same as phi of xy. If you multiply x times y first, and then phi, you would get E prime. If you phi x, phi y, and then multiply them together, you will get E prime. So that means that these two things are equal. So thus you have shown that the property is satisfied for homomorphism. So that means that phi is a homomorphism as indicated, and phi is a homomorphism from G to G prime. If G prime has order greater than 1, if the order is greater than 1 for G prime, that means there are other elements in G prime other than E prime. And phi will not give us those elements because phi of everything that's in G will give us E prime. So that means that therefore phi is not on 2. Hence, we do not have an epimorphism. Also, phi is not 1-to-1 since for any x not equal to y, we have 5x equals 5y equals E prime, because everything is equal to E prime as indicated here, you see. But for 1-to-1, if x is not equal to y, then 5x would not be equal to 5y. That's what we have for 1-to-1. Thus phi is not 1-to-1, and thus phi is not a monomorphism. It's not a monomorphism. All right, the next thing we have is a theorem. All right, this is theorem 3.28. Images of identities and inverses. And we had a theorem with the same name in the previous section. So to be more specific, we would say that this is the images of identities and inverses of homomorphisms theorem. The theorem of images of identities and inverses for homomorphisms. And the theorem begins, let phi be a homomorphism from the group G to the group G prime. If the identity element in G and the identity element in G prime, if E represents the identity element in G and E prime denotes the identity element in G prime, then phi of E is equal to E prime, and phi of X inverse, phi of X inverse is equal to the inverse of 5x for all x in G. So X comes from G, the group that you're mapping from. And E comes from G, the group that you're mapping from. And when you phi the identity in the group that you're mapping from, you get the identity in the group that you're mapping to. And when you phi the inverse of any element in the group that you're mapping from, you get the same thing that you would get if you were to phi the element, and then after phiing the element, then take the inverse. You would get the exact same thing. And this is for all X and G. So your images, you're looking at your images, the image of E would be E prime. The image of the inverse of X would be 5X inverse, because you're going to phi X. We're going to phi X inverse. So that's what we have there for the theorem. And let's go on to the next page. Okay, next page we have example 3. Let's take a look at that. Okay, example 3. Consider the group G of non-zero real numbers under multiplication in the additive group Z, defined by phi such that Z is mapped into G. So this time Z is mapped into G. Up to this point, we've been talking about G as being mapped into G prime. But here we have Z that's being mapped into G. So the Z is really taking the place of the Z of the G, and the G is taking the place of the G prime. So we're mapping from Z into G. So G represents non-zero real numbers. So that would be negative and positive numbers for G. And for G, the set that we're mapping to. And Z, of course, is the integer, so you would have like dot dot dot, -3, -2, or -1, 0, 1, 2, 3 for Z. And this tells us how the mapping occurs here. Phi of n is equal to 1 if n is even, and -1 if n is odd. So that's what we have. That's what phi does. It takes a number and maps it into 1 if n is even. So if n is 2, for example, if n is 2, 5n would be equal to 1. If n is 7, 5n would be equal to -1, because it's -1 if n is odd. Since every integer is either even or odd, and not both, 5n is well defined. So it is well defined. You can easily tell whether it's true or not, because you can easily tell whether the number is even or odd. The following table systematically checks the equality of phi of n plus n equals phi of m times phi of n. So on the left side, you have the operation in the set that you're mapping from. You're mapping from Z. And we said Z was an additive group. So we have addition there. And we're mapping to G. And G is a multiplicative group. So that's why we have G of M times, I'm sorry, phi of M or phi of M times phi of N. So we can look at this in the table. If M and N, we go through the possibilities that we can have here. If M and N are both even, then M plus N would be even. Because if you add two even numbers, you get an even number. Also, if both M and N are even, we would have phi of M, which is an even number. And if you look at what we had above there, if we have an even number, then phi of that number would be 1. You see, so we have a 1 there. And here we're saying they're both even. That's the first case that we're considering. So that means this would be even also. So if n is even, then phi of n, of course, would also be 1. So you would have 1 times 1, and that is the same as phi of n plus 1, because you would have an even plus an even. That would give you an even, and then phi of an even, as you can see from looking at the above equation, phi of an even number would be a positive 1. So you can see that it's true that phi of n plus 1 is it's the same as phi of m. I'm sorry, phi of m plus n. Phi of m plus n is the same as phi of m times phi of n. So we verified this for the next two cases, and that's it. That shows that the property holds and that we have a homomorphism. And then we check for epimorphism and a monomorphism. So once again, one is even, one is odd. Okay, if you have one is even, one is odd, if you add them together, if you add an even number to an odd number, then you would get an odd number. So therefore, we would end up with 1 times negative 1. And that would give us negative 1. And we go on to the next one, which is the last case. If m and n are both odd, if you add two odd numbers, you get an even number. In which case, when you look at the choices that we have, we see that we get negative 1 times negative 1. And if we look at phi of m plus n, if both numbers are odd, all right, then of course m plus n would be even, and then phi of m plus n would be 1. And here we have negative 1 times 1, which is also 1. So that shows completely that the property holds. A comparison of the last two columns shows that phi is indeed a homomorphism from Z to G. However, since phi is not onto, it's not onto because you're going to get all the values in the range from the function. So it's not onto, therefore it is not an epimorphism. Phi is not an epimorphism. And last but not least, since phi of 0 is equal to phi of 2, which equals 1, because they're both even numbers, then phi is not one-to-one, and hence not a monomorphism. Now let's look at example 4. Okay, example 4. Consider the additive group Z and the mapping phi maps Z into Z. So it's mapping the integers into the integers, defined by phi of x equals 5x for all x a member of Z. Since phi of x plus y is equal to 5 times x plus y, which equals 5x plus 5y, which equals phi of x plus 5x. The property, the aforementioned property holds and is true. Therefore, phi would be a homomorphism. And also, it would be an endomorphism because, as mentioned, on the previous page, it satisfies the definition of endomorphism. Clearly, phi is not an epimorphism since phi is not onto. That means that you don't get all the values in the range from the function phi. However, since phi of x equals phi of y implies 5x minus 5y and x equals y, then phi is a monomorphism. That means that phi would be one-to-one, and therefore phi would be a monomorphism. So that's the process you have to go through in the exercises for this section. And for homework, you want to do 1 through 9 odd. So that will give you 5 problems that you need to do in this section. Let's go on to the next page. Next in this section, and the last thing that we have to cover in this section is the kernel. Definition 3.29, definition of kernel. The definition reads as follows. Let phi be a homomorphism. Let phi be a homomorphism from the group G to the group G prime. The kernel of phi is the set ker phi. That's how we symbolize the kernel of phi. It's the set ker phi equals a set of all x, a member of G. So x has to be a member of the group that we are mapping from, such that phi of x is equal to e prime. Phi of x has to be equal to the identity element of G prime, the group that we are mapping to, where E prime denotes the identity in G prime. So that is the definition for kernel. So it's a set. It represents that set, and x, the x's that you have in G, the set that you're mapping from. You phi those x's, and there might be 1, there might be 2, there might be several of those x's that you can phi and get the identity. But every x value that you have in the group that you're mapping from, that maps into the identity in the group that you're mapping to, they would be included in the set. And we have an example here showing you exactly how to find the kernel. And you do have to find the kernel in some of the problems that I just mentioned. To illustrate definition 3.29, which is the definition of kernel. That's what this is. Definition 3.29. To illustrate this definition, we list the kernels of the homomorphism from the preceding example in this section. So in the preceding example, we looked at that and we found out that it was a homomorphism. The kernel of the homomorphism, the homomorphism phi, such that Z is mapped into Z sub n. The kernel defined by phi of x equals class x. In example 1 is given by kernel ker phi. The kernel of phi is equal to a set of all x, a member of Z, such that x equals k times n for some k a member of Z. So when you have a situation using mods, and that's what we were doing in the example mod n. Mod n, when you say n mod n, that would give you the identity when you're working with mods. If you say 2 times n, if you're in mod 4, for example, 4 would be the identity, 0 would be the identity, 8 would be the identity. Any multiple of 4 would be the identity if you're in mod 4. So that's why we have to express this generally, because you don't just have 1 or 2 elements, but you have an infinite number of elements in your kernel. In this case, because x is equal to k times n, for some k that's a member of Z. So Z, that means that k is an integer. So you can have negative numbers as well as positive numbers to k. And that would give you 0, or the identity, as far as this definition is concerned, the kernel. As indicated there, since phi of x is equal to class x is equal to class 0, if and only if x is a multiple of n, the homomorphism phi such that Z is mapped into G, in example 3, defined by phi of n equals 1 if n is even, phi of n equals -1 if n is odd, has the set E, which is the even numbers of all even integers, as its kernel. Since 1 is the identity in G. So that's what we would have for the kernel. The set E of all even integers. For phi such that Z is mapped into Z, defined by phi of x equals phi of x. In example 4, we have kernel phi equals the set whose only element is 0. That's the only element that you get in that set. since 5x equals 0, if and only if x equals 0. This kernel is an extreme case since A of theorem 3-28 assures us that the identity is always an element of the kernel. So this concludes the theory of this section, and we went over the examples there. So you should be able to do the examples in the textbook. And once again, you want to do problems 1 through 9 odd, 5 problems in this section. And you should do some of the problems from the previous section also. I'll let you pick the ones you want to do there, but I would say do about 4 or 5 of those from the previous section also. So I hope that this discussion will be helpful to you in doing the exercises and also in doing the problem that we have from this section on the test. Thank you very much for listening to this presentation. And once again, be sure to copy down the theorems, definitions, and what have you in your notebook from each section. Have a good morning or good afternoon, whichever it is. Bye now.